Welcome back, legends. Get ready, because today we're taking a deep zero to hero dive into the physics of sound. I am absolutely pumped to be your guide through this complete masterclass. We're going to break down the whole shebang, from the absolute basics of how sound actually travels to some truly mind-bending historical physics showdowns. So grab your virtual notebooks, get that focus locked in, and let's make these complex concepts chukka-chuck clear. Let's kick things off with a situation we've all been in. You're trying to sleep, the room is pitch black, and suddenly, you hear it. Where does a mosquito's incredibly annoying buzz actually come from? Like, are they singing a tiny, irritating song with their mouths just to bother you? What do you think is actually happening in the air right around your ear? Well, spoiler alert, it comes from their rapidly vibrating wings. The ultimate truth here is that sound is always, and I mean always, a form of energy created by vibration. Whether it's the frantic flapping of those mosquito wings, a guitar string being plucked, or literally the vocal cords in my throat right now as I speak to you, if there is sound, there has to be vibration. No vibration, no sound. Eggdom simple. All right, here is our roadmap for this explainer. We're going to hit up Number 1, the magic of waves. Number 2, wave properties unpacked. Number 3, a massive clash. Newton versus Laplace. Number 4, factors affecting sound speed. And finally, number 5, echo and reverberation. Let's get into it. Chapter 1, the magic of waves. Now, before we talk about sound specifically, we gotta understand what a wave actually is. Think about dropping a small pebble into a perfectly calm pond. You see those ripples moving outward in expanding circles? That right there is a wave, a disturbance traveling through a medium. And the entire wave universe is basically divided into two camps. On the left side, we have mechanical waves. Sound is one of these, and they absolutely require a physical medium to travel through. We're talking solid, liquid, or gas. On the right side, non-mechanical waves, like light, don't need a medium at all. This is exactly why two astronauts standing right next to each other on the moon can't just chat without radios. No air means no medium, so the sound wave literally cannot exist. But they can see each other perfectly fine, because light travels through the vacuum of space without any issues. So, the crucial point to remember is that waves also move in fundamentally different ways. Light is what we call a transverse wave. That means the particles vibrate up and down, completely perpendicular to the direction the wave is actually traveling. This creates peaks called crests and valleys called troughs. But sound? Sound is different. It's a longitudinal wave. Imagine a super crowded area, like a train station, where people suddenly get pushed. The particles bump into each other parallel to the wave's direction. They clump together super tightly in what we call compressions, and then they spread far apart in rarefactions. So sound travels as these alternating high and low pressure zones. Moving on to Chapter 2, Wave Properties Unpacked. Before we start calculating speeds, we need the vocabulary. First up is amplitude. Imagine a particle just resting quietly on that center zero disturbance line. When a wave passes through, the maximum physical distance that particle gets pushed, either up or down from that center point, is its amplitude. And in the real world, amplitude dictates loudness. The harder you shout, the more energy you're packing in and the higher that amplitude peaks on the graph. Next is frequency. This one is simple. It's literally just the number of complete vibrations, or oscillations, that happen in exactly 1 second. We measure this in hertz. And guys, here is a golden rule, a total brahmastra for you to remember forever. Frequency is purely a property of the source. It does not change even if the sound bounces off a wall or moves from air into water. Whatever object is creating the vibration, that dictates the frequency. Period. And then we have wavelength. Just like it sounds, it's the actual measurable physical distance between two consecutive compressions or two consecutive rarefactions. Now, let's tie all these properties together to reveal the ultimate wave formula. Ready? Speed equals frequency multiplied by wavelength. Think about it. If you know how many waves pass by in a single second, and you know how long each of those waves is, you know exactly how fast that wave is flying through the air. All right, Chapter 3, the historical showdown, Newton versus Laplace. Oh, you're gonna love this one. It's the story of two absolute scientific heavyweights. Look at step 1. Sir Isaac Newton assumes that sound travels so normally that the temperature of the air stays completely constant. We call that an isothermal process. Based on this, in step 2, he cooks up a straightforward formula using atmospheric pressure divided by density. But decades later, Pierre-Simon Laplace steps into the ring for step 3. Laplace points out a massive oversight.
He says, wait a minute, when sound waves tightly compress the air, those particles get packed together like a crowded mall on a Sunday. This friction naturally generates heat. And because sound travels so fast, that heat actually has no time to escape. So it's not isothermal, it's an adiabatic process. So for step 4, Laplace adds a vital multiplier to Newton's math, a little symbol called gamma, to account for those heat changes.
It is honestly fascinating how authority works in science. I mean, because it was Sir Isaac Newton, the legend himself, making this isothermal assumption, everyone just blindly believed him for a really long time. He stated that sound travels without changing the temperature of the medium, and the whole scientific community just nodded along. Yes, sir, Mr. Newton, even though his core assumption was actually a bit flawed.
But there was a glaring problem that they couldn't ignore forever. Newton's isothermal assumption meant his formula calculated a speed of exactly 280 meters per second. And this left scientists totally scratching their heads. Real-world observations, basic experiments, they all showed sound was significantly faster than 280. They knew his number didn't match reality, but they just couldn't figure out why. Well, until our next hero arrived on the scene. Laplace came along and completely revolutionized the calculation with a massive brainwave. He confidently declared that sound travels so incredibly fast that heat simply cannot exchange with the surroundings during those rapid compressions. It is an adiabatic process. He realized that these tiny rapid temperature changes actually affect the elasticity of the air itself. Total game changer. By applying that adiabatic correction, specifically adding that gamma multiplier of 1.4 for air into Newton's original formula, Laplace absolutely nailed it. He calculated the accurate speed of sound at around 330 to 332 meters per second, perfectly matching real-world experimental data. Newton laid the foundation, but Laplace perfected it. And this right here is exactly why we constantly test and refine our knowledge. Chapter 4, Factors Affecting Sound Speed. Let's see what happens out in the wild. So we have the formula, but what environmental variables out there in the real world actually change this speed from day to day? Let's break it down. First, density. If a gas gets denser, sound actually slows down. It's inversely proportional. Second, temperature. If you heat the air up, sound speeds up about 0.61 meters per second faster for every single degree Celsius rise. Third, humidity. Okay, pay attention because this is a classic trick question. Adding moisture to air actually makes it less dense. Think of it like mixing pure thick milk with a bunch of water. You lower the overall density of the mixture. Because moist air is lighter, sound travels faster through it. Finally, wind. This one's intuitive. If the wind is blowing in the exact same direction the sound is traveling, it naturally carries the sound faster. Now, let's play Mythbusters for a second, because exams absolutely love to trick you with these. The following factors do not change the speed of sound. A massive misconception is atmospheric pressure. Listen, if you double the pressure, the density of the gas doubles right along with it. They cancel each other out in the formula, meaning zero change to the speed. What about amplitude? Nope, that only changes how loud the sound is, not how fast it goes. And wavelength and frequency? If you increase the frequency, the wavelength just gets shorter to compensate. The overall speed remains perfectly constant for that specific medium. Finally, Chapter 5, Echo and Reverberation. So what actually happens when those sound waves crash into a massive obstacle, like a distant hill or the solid walls of a grand hall? First, let's clearly define an echo. An echo is hearing a distinct, clear reflected sound only after your original sound has completely stopped. Imagine you're standing on a mountain edge and you enthusiastically yell a name, like Sonam. You completely finish speaking, there's a brief silent pause, and then the distinct reflection arrives back across the valley. Sonam! That is an echo. But notice the highly specific critical number here, 17. Our human ears and brains are wired in a way that we need a minimum time gap of 0.1 seconds to actually distinguish between two separate sounds. If the reflection arrives faster than that, it just blurs into your original shout. Now, since sound travels at roughly 340 meters per second, for the wave to travel out, hit an obstacle, and bounce all the way back in exactly 0.1 seconds, that reflecting wall must be a minimum of 17 meters away. Boom. That is precisely why you don't hear dramatic mountain echoes in your small bedroom. But wait, what if the walls are close, and there are a lot of them, and they're completely bare? That brings us to reverberation. Unlike a clear echo, reverberation is the persistence of sound due to repeated, overlapping reflections from multiple surfaces.
This is that booming, lingering gunge or resonance you experience in a small, empty room when you just move in, or a massive stone structure like the Taj Mahal. The sound waves are frantically bouncing off the floor, the ceiling, and the walls simultaneously, creating a continuous, lingering blur of overlapping sound. And that brings us to the end of our masterclass, Legends. But before we wrap up this explainer, I want to leave you with a final thought experiment to really test what you've learned. So bats use biological sonar, right? They shoot out ultrasonic sound waves to hunt in pitch darkness. Based on everything we've talked about today, what happens if a bat sends out a sound pulse and the wave never ever bounces back as an echo? What does that bat instantly know about the physical space directly in front of it? Think about it. Understanding these ways isn't just textbook stuff. It's literally how creatures survive in the real world. Thank you so much for joining me today. Keep questioning, keep learning, and I'll catch you in the next explainer.